So any questions to have? Yes, someone has eaten something. Yes, so we have in the last class we have learned this thing is called function of random variable. So few problems we have done there, and one another problem I will do today. And after I finish the special distribution, so special discrete distribution has been done. After I finish the special continuous distribution, after that we will do some more problems on the function of random variable. Is it okay? Okay, so before I go to there, just one thing. Shubham Kumar is here. Shubham Kumar, are you here?
Hello, sir.
Yes, Shubham Kumar. So in the Moodle test score list, we didn't see your name. So that's why.
But I gave the test.
Okay, I will talk to the coordinator. Then let's see what can be done.
Okay, sir. Okay.
Okay, so it's 12:1. So can all of you see this one more page?
Yes, sir.
So this was the result we stated in the last class. So this is about the random variable. So this is about the function of random variable. I once again I will state the result. Okay. So and with that I have done already one problem. Another problem I will do today. So that's phi be a differentiable strictly increasing. So do you know what is the meaning of strictly increasing? Okay, I forgot to tell you this. Do any of you know what is the meaning of strictly increasing or decreasing? No one knows?
Derivative is always greater than.
Sorry, I can't hear you. Sorry?
So f dash x is always greater than or equal to 0 for
Okay,
a strictly increasing function.
Yeah. So
And vice versa for a strictly
this is this is one condition. This is sufficient and necessary condition, but this is not the definition. This is right. Whatever you have said is right. That the phi prime of some point will be definitely positive. Okay, if it is strictly increasing, and if it is strictly decreasing, then this phi prime of that point will be negative for all points. But this is true when we are considering that the phi is a differentiable map. But the definition of strictly increasing doesn't involve differentiability. So without using the differentiation, can you define?
Phi b greater than phi a when b greater than a, and similarly for less than.
Very good. So this implies a greater than b implies phi a greater than phi b. And whenever I say increasing, in this case, a greater than b implies phi a greater or equal to phi b. So let phi represent the image of phi. And phi inverse the inverse function to phi. let x be a continuous random variable having density f such that if x equal to 0, so outside the interval, the intensity function is 0 for all x not equal to I, then y equal to phi x has density g given by g of y equal to 0 for all y doesn't belong to the image of the interval phi I, and this is equal to f of phi inverse of y, the mod of d dy phi inverse of y for y belongs to phi I. Okay, so this is the result. So which we will use, this can be deduced easily, this is not difficult, but I am not doing the proof of this. But this is not theorem 1, there is no other theorem, so just theorem. So this result I will use now to solve the problem. So let lambda be a random variable. So not lambda, this is a random variable with an exponential density with parameter lambda. Find the density of x for beta 1 by beta, sorry, not beta, 1 by beta for beta not equal to 0. So this is the function in our case. Okay, so the function is y equal to x power 1 by beta. So can you say whether the function y is strictly increasing or decreasing? Okay, before going to that, just let's see what is the density function fx. This is exponential density with the parameter lambda. So fx is equal to lambda e power minus lambda x for x greater than 0 and 0 for x less than 0. So we need to consider only, so we need to consider, check that phi x equal to x power 1 by beta for some beta not equal to 0 is differentiable and either strictly increasing or decreasing for x greater than 0. Okay, so tell me for x greater than 0 whether the phi function is increasing or decreasing. Whatever you think.
Decreasing.
Is it decreasing? So suppose beta equal to uh, take 2. Okay, then this will be x power 1 by 2. Then what do you think? What do you think? What is x power 1 by 2?
This is root function, square root function, so its graph will be decreasing.
No. Graph is increasing, right? Okay, let's check whatever you said. So if we take the differentiation of this thing, this will be half 1 by x power half minus 1. Okay, sorry, half. So this is always increasing, greater than 0 for all x greater than 0. So phi function is always increasing. Phi function is strictly increasing. This is not only for 2. If you take any beta greater than 0, you will get this thing. Okay, and if you take beta less than 0, again get phi x equal to x power 1 by half. So if you take the phi inverse of x, take the differentiation of phi inverse of x, you will get 1 by beta, again the same thing, 1 by x power 1 by beta minus 1. So this is for x greater than 0. So this thing is less than 0 as beta is less than 0. So phi is strictly decreasing. So is it okay? So this depends only upon whether beta is greater than 0 or less than 0. So if you fix beta, this function phi x is always strictly increasing or strictly decreasing for the whole interval x greater than 0. Okay, so we can apply the previous theorem and we get that here phi x equal to x power 1 by beta for x greater than 0. Put this as y. So x equal to y power beta. So dx dy equal to beta y power beta minus 1. And so what is the density function of y equal to fx? Phi x. This is gy equal to see what is this thing? This is f of phi inverse of y mod dx dy for y greater than 0, 0 or y less equal to 0. Okay, so this will be y power beta minus 1 just 1 second. Mod beta, there is also one mod beta, and then if lambda, this comes from this part, this gives lambda e power minus lambda y power beta. So this for y greater than 0 and 0 for y is equal to. Is it okay to all of you? Any questions? Now, so this problem is done. So we'll go back to the thing we are doing, that is the continuous, special continuous distribution. So we'll go back to there. So in this case, we have already done. A was uniform, B was Cauchy. Now the third thing, what we'll be doing now is exponential. So this thing we have seen before. If you remember, so we did one problem in the last class that if x is uniformly distributed, so can anyone tell me what? Okay, from this we told me before. So I'm not asking you. So x is what uniform distributed on 0, 1. So this means that fx equal to 1 for x belongs to the open interval 0, 1 and 0 otherwise. Okay, so y equal to another random variable you are choosing, y equal to minus lambda inverse log 1 minus 6 for lambda greater than 0, for some lambda greater than 0. Find the, then using the theorem, the previous result, the density function of y is gy equal to lambda e power minus lambda y for y belongs to 0, infinity, and 0 for y is equal to 0. So this we will get, and this is called exponential density. This we have also just seen. So this is called exponential density. So the corresponding distribution function is fx equal to minus infinity to x, f of x dx. This will be equal to, this is obvious, 1 minus e power minus lambda x for x greater than 0 and 0 for x less equal to 0. So this is the distribution function of the exponential density or exponential random variable. Now, this exponential distribution means some random variable is have this exponential density, then we say that this random variable is exponentially distributed. Now, the exponentially distributed random variables are useful in studying. Just write this thing. These are useful in studying decay time of radioactive particles. This is something which we have seen in the beginning of this course. some example we did. Decay time of radioactive particles so this is also studying useful for studying models about the time until a piece of equipment fails. Or the time and equipment takes to complete a job, something like that. So for these cases, these density function or these random variables are useful. So this has some properties which has some practical implication. So properties is probability of x greater than a plus b equal to probability of x greater than a into probability of x greater than b. For a, b greater equal to 0. So this is very easy to prove. So what is p of x greater than a plus b? Can anyone tell me? What is this? So this is equal to 1 minus fx. 1 minus x a plus b. That is 1 minus e power minus 1 minus 1 minus e power minus lambda a plus b, which is equal to e power minus lambda a plus b equal to e power minus lambda a into e power minus lambda b. This is equal to similarly x greater than a into p x greater than b. So from this follows immediately that the conditional probability that px greater than a plus b with the condition that x is greater than a equal to probability that x greater than b. So this has some practical implication. So suppose x is the random variable denoting the time of a machine. Takes to fill after installment. So installation. Installation. If there is no failure, till time a, then probability of failure in next b units of time of failure in next b unit of time so the conditional probability is equal to the unconditional probability. The unconditional probability of no failure in first b units of time. Okay, so that means we know that the machine will failure after time a. In that case, the conditional probability that the machine will failure after time a plus b is same as that the machine will failure after time b, the unconditional probability. C also follows immediately from B. That is okay. C is not obvious, but this is the converse of the previous two things. That is x greater than a plus b. The probability of this equal to probability that x greater than a into probability that x greater than b implies p x greater than 0 equal to 0 or x is exponentially distributed. Okay, this is the end of the distribution, exponential distribution. Any questions before we go to the next special continuous distribution? Any questions? Bishop Shahu, any question? Bishop Shahu, are you there? Okay, so you must have noticed that in previous all cases we are also computing the mean and the variance of the special continuous distribution. But in this case, for exponential density function or exponential distribution, we haven't computed the mean and the variance. The reason is that next we are going to introduce some other special continuous distribution, which is a more general case of the previous one, that is the exponential distribution. And for this more general distribution, which is the gamma density function or gamma distribution, we will compute the mean and the variance. So from here, the mean and the variance of the exponential distribution will be just a particular case. So this is our next special continuous distribution, which is called gamma density or gamma distribution. Here again, like the previous cases, we will that give the density function. So gamma density function is which is denoted by this gamma, x, alpha, lambda. These are the parameters, alpha and lambda. So this will be alpha power lambda, lambda power alpha by gamma alpha, x power alpha minus 1, e power minus lambda x. So this is true for x greater than 0, and this is 0 for x is equal to 0. Now put alpha equal to 1. Then you will get lambda gamma 1 x x e power minus lambda x for x greater than 0 and 0 for x is equal to 0. Okay, what is gamma 1? Can any of you tell me what is gamma 1 or what is the gamma function?
1.
gamma 1 is 1. So this will be equal to lambda e power minus lambda x for x greater than 0 and 0 for x less equal to 0. So this is, you can see, is the exponential density. Now the question you may ask, so can you ask any question here? Any question you want to ask or you should ask here? You can ask that why you are using, you are multiplying by this particular constant. That you can ask. So we have seen this thing before, that is, if we have a non-negative function whose integration from minus infinity to infinity is finite. In this case, if we so this I was saying, so suppose x is greater than fx is greater than 0 for all x, and c equal to minus infinity to infinity f of x dx is finite, then gx equal to 1 by c fx gives a density function. Okay, so in this case also, if we just take this thing, take this minus infinity to infinity x power alpha, sorry, minus infinity to infinity x power alpha minus 1 e power minus lambda x dx, and compute this integration. So put y equal to lambda x and then this will be 1 by lambda power alpha minus infinity to infinity y power alpha minus 1 e power minus lambda, not lambda y, e power y by. Okay, so this is not from, okay, this is also not from minus infinity to 0, this will be 0 to infinity. Again, this is 0 to infinity. So this is 0 to infinity as if lambda is greater than 0. So, so is this integration, does it converge? This one, does it converge? Integration 0 to infinity y power alpha minus 1 into e power minus y dy. Does it converge?
This is gamma alpha.
Okay, gamma alpha, fine. So gamma alpha, does it converge for all alpha? So this converges if alpha greater than 0. Okay. So otherwise, this does not converge. So whenever we take, so that's why we multiply, but this we divide this x power alpha minus 1 e power minus lambda x, we divide by gamma alpha by lambda power alpha, and we assume alpha greater than 0, lambda greater than 0. Okay, and we get, this is the, this gives the gamma density function. with parameters lambda and alpha. Okay. Okay, so do you know any properties of the gamma function? Any properties you know? Any of you?
Gamma n plus 1 is equal to n gamma n.
Right. Any other properties? Gamma half equal to root pi.
Yes, sir.
So moment generating function is the next thing of this density function. So here mt equal to, so you know this is the exponential of, sorry, expectation of e power tx. So this is 0 to infinity e power tx, and you multiply this with the density function. So this is equal to 0 to infinity lambda power alpha by gamma alpha x power alpha minus 1 e power minus lambda minus t x dx. Now substitute this lambda minus t x by y. So we will get this is equal to 0 to infinity lambda power alpha by gamma alpha 1 by lambda minus t power alpha y power alpha minus 1 e power minus y dy. Here we assume lambda minus t is greater than 0. So we will get this is equal to lambda power alpha by gamma alpha. We can also take out this lambda minus t power alpha 0 to infinity y power alpha minus 1 e power minus y dy. And this will be gamma alpha. So we will get lambda power alpha by lambda minus t power alpha. And we will assume here that lambda greater than t. Okay. So this is the mt. Okay. So if we take the, so to find the moments, we have to take the integral differentiation of mt, then put t equal to 0. So this will be alpha lambda power alpha by lambda minus t power alpha plus 1 and m double prime t equal to alpha alpha plus 1 into lambda power alpha by lambda minus t power alpha plus 2. So the mean is m prime 0. So this will be alpha by lambda, and the variance is, sorry, the moment is second central moment. So ex square, the expectation of a square, equal to m double prime 0. This will be alpha alpha plus 1 by lambda square. So the variance is the sigma square equal to ex square minus ex the whole square. So this will be alpha by lambda square. So this way we have got the mean and the variance of the gamma density gamma distribution. From this, can we get the mean and the variance of the exponential distribution? Can you tell me? Can any of you tell me from this? Can you get the mean and the variance of the exponential distribution? So exponential density,
If we put alpha is equal to 1.
right, is obtained from the gamma density if we put just 1 second, alpha equal to 1. Just 1 second. Hello? Hello? না ঠিক আছে হ্যাঁ বা yeah, sorry. So if we put alpha equal to 1, so for the exponential density mean equal to 1 by lambda and variance equal to 1 by lambda square. Okay, so something like binomial distribution, we have seen that if we can, if two distributions which are binomial, if they are independent, in this case we can take their sum, that is again binomial, and we know what will be the parameters of this binomial, which is the sum of the given binomials. So similar things are also true for gamma distribution. So let x1 is to xn be independent random variables suppose for I equal to one to n, xi has as a gamma alpha I comma lambda distribution. So and let y equal to the sum of this xi then y has again a gamma distribution and the parameters are summation alpha I equal to 1 to n comma lambda distribution. So what I said that the similar things also happens for binomial distribution. Okay, if you have any question, please ask me. Otherwise, I will now go to the next topic. So there we have taught in the last class that is called Poisson process. Now there is a relation between the Poisson process and the gamma distribution. So that is the relation what we will study now. So relation between Poisson process and gamma distribution. So remember that NT here is the number of events we count up to time t. So from this we can make some other random variable. So like t1 is time for the first event. T2 is time for second event. After the occurrence of the first event. And Ti is, so similarly you can define Ti, time for the ith event, after the occurrence of the I minus 1 first event. I minus first event. So these TIs are called inter-sequence of inter-arrival times. Okay, now we will find what is the distribution of these TIs. So first start with the distribution of T1. Okay, so T1 is equal to T. This is the distribution of T1. Right. So this is 1 minus T1 greater than T. So what does it mean that T1 greater than T? So this is 1 minus probability that no events occur in the time interval 0, t. Okay, now you tell me, so this is equal to 1 minus P nt minus n0 equal to 0. Right? So what is n0? For Poisson process, what is n0? Can any of you tell me?
0.
N0 is 0. So we'll get nt equal to 0. And what is the probability that nt equal to 0 for Poisson process? We know this. This is e power minus lambda t. Okay. So we can see that T1 has exponential distribution with density lambda e power minus lambda t. Okay, any questions? Okay, so we'll go to the next thing, that is T2. Only these two things we will do, and other things will be similar. So I'm not doing here. So we want to find the distribution of T2. So we want to find the probability that T2 less equal to T. So this is again 1 minus probability that T2 greater than T. Now this you can find in some other way. So T2 greater than T, suppose that, see that here T2 greater than T, this depends upon also the T1, right? So T1 can be anything. The first event occurs at any S point, at any time S. So this will vary, and also considering that we will for T1 equal to S, we'll consider the probability that T2 will be greater than T, where T1 equal to S. And we have to take the sum of all these things, or the integration. Okay. So have you understood? So T2 greater than T, so that means T1 can be anything. So T1 equal to some time is, and we have to take this integration. In other words, this is equal to expectation of probability T2 greater than T with condition T1 equal to S. And here, because T1 equal to S, this is varying, so with density function of T. Okay, any questions you have here? This may not be very easy for the first time, but if you think this is true, okay, whenever we consider T2 greater than T, that means we have to also consider T1 is fixed at some S. But this S also varies. So that's why we take all these probability we take, that is T2 greater than T with the condition T1 equal to S. All this probability we take and take the integration of all these probabilities, or take the summation of all these probabilities. So that's why we are taking the expectation of the function, which is the probability T2 greater than T with condition T1 equal to S. And here we take the expectation with respect to the density function of T1, because T1 equal to S is adding. Is it okay? Now we will compute what is T2 greater than T with T1 equal to S. So this is equal to probability that 0 events in the interval S plus in S comma S plus T with the condition T1 equal to S. Now this is equal to probability 0 events in the interval S comma S plus T. And this is because these events are independent. So this we call, this is one property of the Poisson process. So all these events are independent. One doesn't depend on the other. And this we know, this is equal to e power minus lambda t. Again, because this thing depends only on the length of the interval. So S comma S plus T and 0 comma T have the same probability. So from here you can see, you can show T2 greater than T equal to e power minus lambda T. So T2 less equal to T equal to 1 minus T power minus lambda T. In general, probability Ti less equal to T equal to 1 minus T power minus lambda T. So this is the distribution of all these Ti's. Okay. From this, we can get another distribution, another random variable. So let Wn be the waiting time until the nth occurrence so Wn equal to summation Ti where I equal to 1 to n. Each Ti has exponential gamma lambda distribution. So what is exponential means? So this is equal to gamma 1 comma lambda. Okay, and Wn is the sum of all these Ti. So Wn has. So what will be the distribution of Wn? Any of you? Just the result we have seen. So take the sum of all these gamma distribution, gamma alpha comma lambda, and take y equal to summation xi, and xi is our independent random variables. Then y has gamma summation alpha lambda distribution. Here each, for our case, each alpha equal to 1. So we will get gamma n comma lambda distribution. Gamma so the expectation of Wn equal to expectation of all these Ti. So this will be n by lambda, and variance of Wn equal to n by lambda square. Now observe that at least n events has occurred. Up to time t equal to occurrence time of the nth event is less equal to t. So from that, this will give the probability that is n t greater than equal to n t. Sorry, n t greater than equal to n is equal to probability that Wn is equal to t. So this is summation k equal to n to infinity p n t greater than equal to k equal to, we know the distribution of Wn, so this is 0 to t lambda power n x power n minus 1 e power minus lambda x dx by gamma n. So this will be equal, this gives summation k equal to n to infinity e power minus lambda t power k by k factorial equal to 0 to t lambda power n x power n minus 1 e power minus lambda x by gamma n dx. So this is one equality we are getting from this gamma distribution and the Poisson process. Okay, just one problem I will do here, then we will finish up together. Just one problem. So problem on the, it's called Poisson process. So let NT be a Poisson process. T greater equal to 0, Poisson process. With lambda equal to 0.5, find the probability of no arrival in the interval 3, 5 and find the probability that there are exactly one arrival. So here arrival means the same as the occurrence of that event. One arrival exactly one arrival in each of the intervals zero comma 1, 1 comma 2, 2 comma 3 and 3 comma 4. Okay, so the answer is, the first one is very easy, that the probability of no arrival in 3 comma 5. So we know that probability of n t plus s minus n s equal to n is equal to minus, this probability is equal to minus half t, because this has Poisson, this is a Poisson process with parameter lambda equal to half t power n by n factorial. In our case, s equal to 3, t equal to 2, n equal to 0. So p n5 minus n3 equal to 0. This has probability e power minus half into 2, half into 2 power 0 by 0 factorial. So this will be equal to e power minus 1. And the second case is, this is A, this is the B case. So find the probability that there are exactly one arrival in each of the intervals 0, 1, 1, 2, 2, 3, and 3, 4. So suppose T in one classes here T equal to 1 minus N is equal to 1. This is equal to e power minus half T. Okay, T equal to 1 here. So this again we put 1 into half into 1 power 1 by 1 factorial. So this is equal to e power minus half by 2. And here s equal to 0, 1, 2, 3. This is because we have taken the probability that there are exactly one arrival in each of the intervals 0, 1 is equal to 0, is equal to 1, is equal to 2, is equal to 3. So now the total probability is the probability that exactly one arrival in each interval, this will be equal to the product of all these things. So s equal to 0 to 3 e power minus half by 2. So e power minus half by 2 power. Okay, so I stop here. Some more problems we'll do in the next class, and we'll try to finish as much as possible this special continuous distribution. Okay, any questions? If you have no questions, you may leave. Others can ask me questions. Okay, so if you have no questions, then we stop the lecture here.